Hello, I hope I am audible. We can start the lecture in couple of minutes since if few more students arrive, or else we will start by 7 or 5. I think we can start today's session. I hope I am audible. If I am not audible, you can just write it in chat box also. The first question that we are looking on is from GATE 2015 Chemical Engineering GATE paper, and the question number is 23. The question is: two infinitely large parallel plates 1 and 2 are held at temperatures T1 and T2, where T1 is greater than T2 respectively, and placed at a distance 2D apart in vacuum. Infinitely large flat radiation shield 3 is placed in parallel between 1 and 2. The emissivities of all the plates are equal. The ratio of the steady state radiative heat flux with and without shield is dash. So So here we have been given two infinitely large parallel plates, 1 and 2, where we have been given the temperature relation, that is T1 is greater than T2, and they are placed at distance of 2D, 2D in vacuum. So between these two plates we are inserting a radiation shield. So this is our radiation shield. So the purpose of this radiation shield is to decrease the radiation heat transfer between two of these large parallel plates 1 and 2. And here we have in the question we have been asked to find the ratio of steady state radiative heat flux with and without field. That is Q upon H my heat flux. So the ratio of with shield upon Q upon A without shield. So we have to find this ratio. So there is a straight away formula for this case. So let's say if I am having two infinitely large parallel plates, this is my first plate, this is my second plate, and if I am inserting radiation shield between these two plates, let's say this is my first radiation shield, second radiation shield. Similarly, I can put n number of radiation shield in between these plates. So corresponding to n, the ratio of this heat flux with shield upon ratio of heat flux without shield will be equal to. So is there noise in my audio or is it breaking? I'm not sure if this will solve the problem or not. So from the next question, I will just play the online solution. Maybe that will be clear. So this ratio is given by 1 upon n plus 1. And here in this question, we have been given n equal to 1. We are only having a single plate in. We are having a single plate in between them. So for this case, this ratio will become 1 by 2. That is 0.5. From the given option, we can select option A corresponding to this ratio is 0.15. So just to revise, radiation shield is a barrier wall of low emissivity placed between two surfaces which reduce the radiation between two bodies. So as mentioned in the earlier question, these were our two infinitely large parallel plates and we were inserting these three radiation shield in between them. Then the heat flux with shield will be 1 upon n plus 1 times heat flux without shield. So we used this formula to find that ratio and the final answer was 0.5. Option A, which was 0.5. So if you have any doubt, you can write it in chat box or speak up, or else we can start with the next question. The next question is question number 49 from GATE 2015 Chemical Engineering paper. In the question is, a heated solid copper sphere is immersed in a large body of cold fluid. Assume the resistance to heat transfer inside the sphere to be negligible and the heat transfer coefficient H, density rho, and heat capacity C, and the thermal conductivity K to be constant. Then at time t, the temperature difference between the sphere and the fluid is proportional to which of the following options. So basically this is the case of lumped heat capacity analysis. You can straight away remember the formula for this or else we can derive this very easily. So let's look at the video solution for this question. I have stopped sharing the screen. Just let me know if there are issues related to this video last time. See? Okay. Just wait a minute. Negligible, and the heat transfer coefficient H. Hello everyone. We are looking at question. air and the fluid is proportional to this the exponential of minus HAT upon rho C. So from the given option, we can see that option A is correct. That is temperature difference will be proportional to exponential of minus of HAT upon rho C. Rho V C. That is, we will select option A as the correct. Okay, so we looked upon this question related to the derivation of the Salomon heat capacity analysis. So basically, you can just straight away remember the formula for this case also. So it will be T upon T infinity minus of T upon T naught is equal to exponential of minus of HAT upon rho Vc. So this formula will only be applicable when we have been given this term. Okay, this assumption, that is the resistance to heat transfer inside the sphere, will to be negligible, and this means that the Biot number should be less than zero point 0.1. If Biot number is less than 0.1, then only we can use this formula straight away. Now let's look at this second question. This is question 50 from GIT 2015 from chemical engineering, and in this question we have been given an external flow over the cylinder, and we have been given the parameters Nusselt's number correlation, and we have been asked to find the rate of heat loss per unit length from pipe to air. So let's look at the video solution. Hello everyone, we are looking at question 50 of GIT 2015 chemical engineering paper on the subject of heat transfer. The question is, air is flowing at a velocity of 3 meters per second perpendicular to a long pipe, as shown in figure below. The outer diameter of the pipe is 6 cm and the temperature outside the surface of the pipe is maintained at 100 degrees Celsius. The temperature of the air far from the tube is 30 degrees Celsius. And we have been given data corresponding to the system, international single correlation, and we have been asked to find the rate of heat loss per unit length from the pipe to air. Let's look at the solution. So here we have been given Nusselt's number correlation. Nusselt's number is H upon K is 0.024. Reynolds number is 2.5. So from this equation we can get H, and then we have been asked to find Q upon M. So that is, we can find it as H A delta T, where delta T will be this 100 degrees Celsius minus 30 degrees Celsius is the temperature difference. Basically, from the Nusselt's number correlation, we will be getting the heat transfer coefficient, that is putting in this energy balance equation to find the heat loss per unit length. So to calculate H, let's just calculate Reynolds number. So Reynolds number is defined as rho V upon mu. Here we have been given the kinematic viscosity. Let's just replace the values over here. The velocity is 3 meters per second. Diameter of the pipe is 6 centimeters. So we looked upon this question related to external flow over the cylinder, in which we had to find the heat loss per unit length. So we used this Nusselt's number correlation. For that, first we calculated the Reynolds number. Then from the Nusselt's number correlation, we calculated the value of this heat transfer coefficient, and on the basis of that, using this formula Q is equal to HA delta T, we find the heat loss per unit length. So now let's take a look at this question 11 from GATE 2014. The question is, in a completely opaque medium, if 50% of the incident monochromatic radiation is absorbed, then which of the following statements are correct? So option P is 50% of the incident radiation is reflected. Option Q is 25% of incident radiation is reflected. Option R is 25% of incident radiation is transmitted. Option S is no incident radiation is transmitted, and we have to select the correct option from the given. So here we have been given that this is an opaque medium. So when we say opaque medium, that means if radiation is incident on this, none of this radiation will get transmitted. Okay, so since this is an opaque medium and no radiation will be transmitted by this, Okay, let's start again. So here we have been given an opaque medium, and then radiation is incident on this surface. And since this is an opaque medium, the none of the radiation will get transmitted beyond the, in this opaque medium. That is, the transmissivity, we denote it by tau, will be 0. And for any medium, we can write this alpha. Alpha is absorptivity plus transmittivity plus rho is reflectivity will be equal to 1. Now in this question, tau is 0, so we can cancel this term. And we have been given that the 50% of monochromatic radiation is absorbed. So that is alpha. From here, we can write that alpha equal to 0.5. That is, we can write 0.5 plus rho is equal to 1. That implies rho, which is reflectivity, is equal to 1 minus of 0.5, and it will become 0.5. So from the given options, this 50% of radiation is reflected. This is a correct option. Option Q is 25% of radiation is reflected. This is incorrect. Option R is also incorrect. Then option C is no incident radiation is transmitted. This is correct option. So from the given option, we can select this P and S as the correct option, that is corresponding to option A. So for this given question, we can select the correct option as option A. So now let's look at the next question. So this is question 33 from GATE 2014 paper. Since my voice is breaking, I will just play the video solution only. Hello everyone. We are looking at question 33 of GATE 2014 chemical engineering paper, and the question is: a brick wall of 20 centimeter thickness has thermal conductivity of 0.7 watt per meter per Kelvin. An insulation of thermal conductivity 0.2 watt per meter per Kelvin is to be applied on one side of the wall, so that the heat transfer to the wall is reduced by 75 degrees Celsius. The same temperature difference is maintained across the wall before and after applying the insulation. The required thickness in insulation in centimeter is dash. So here initially we have been given a brick wall, and later we are insulating the brick wall from one side, keeping the temperature difference in both the cases same. So we have to find the thickness of the insulation such that the heat transfer of the wall is reduced by 75%. So if we look at this case 1, we have this brick wall, and A we have been given as 0.7, thickness is 20 centimeter. Now in case 2, this brick wall will remain same, and we are adding an insulation. For this insulation, the thermal conductivity is 0.2 watt per meter Kelvin, and its thickness we have to find. Now, the temperature difference is same for both the cases. So let's say temperature over here is T1, here it is T2, and in this case also the temperature in this case here will be T1, and outside the insulation will be T2. So the heat flux we can write it as Q upon A is equal to delta X upon K. Not like that. We can basically write it as minus of Ka dt upon dx. That is, we can write this in terms of delta T upon delta X and this term we call it as resistance. That is delta T upon R. Now for case 1, let's just call this as resistance R1, R1 and R2. So for case 1, we will be having the single resistance, and you can find it formulas R1 is equal to delta X upon K. Here delta X is the thickness of the wall that we have been given as 20 centimeter, basically 0.2 meter. For the thermal conductivity, we have been given as 0.7. Let's just keep the area as area. Now for case 2, the total resistance will be sum of R1 and R2. It is R1 plus R2. R1 we have found it out as 0.2 1.7 into 8 plus R2 we have thickness we have to find. Thermal conductivity we have been given as 0.2 into area. Now we have the resistance for both of these cases. Now in the given question we have been given that the heat transfer to the wall is reduced by 75%. That is, we can also write this as Q2 will be 25% of Q1. That is, Q2 is equal to 0.25 Q1. Now Q2 is delta T on R and 0.25. Q1 is delta T upon R1. Delta T, that is temperature difference across both the cases, we have been given same, so we can cancel that. That is, we will be having R on R1 is equal to 1 upon 0.25 equal to 4. Then R we can replace it as 0.2 by 0.7 plus T upon 0.2 and that will be divided by 8. For R1 is 0.2 upon 0.7, 1 upon 8. This 1 upon 8 will get cancelled. We will be having 2 upon 0.7 plus T upon 0.2 is equal to 4 by 0.7. That is basically 5 times thickness will be equal to 3 into 0.2 on 0.7. This will be equal to, thickness will be equal to 6 upon 35. This will 6 upon 35 will come somewhere around 0.1714. This is in meter, so thickness in centimeter will be 17.14 centimeter. That is the required thickness of the insulation in centimeter is 17.14 centimeter. So we will put the final answer as 17.14. We looked upon question 33 of GIT 2014 chemical engineering paper. This was related to conduction and the insulation. Now let's look at the another question. This is question 2014 from GIT. This is question 34 from GIT 2014 chemical engineering paper, the subject of heat transfer. And this is related to a double pipe counterflow heat exchanger, in which we have to find this minimum heat exchanger area. We'll again play the video solution. Hello everyone. We are looking at question 34 of the 2014 chemical engineering paper. And the question is: an oil with a flow rate of 1000 kg per hour is to be cooled using water in double pipe counter flow heat exchanger from a temperature of 70 to 40 degrees Celsius. Water enters the exchanger at 25 degrees Celsius and leaves at 40 degrees Celsius. The specific heats of oil and water are 2 kJ per kg Kelvin and 4.2 kJ per kg Kelvin. The overall heat transfer coefficient is 0.2 kilowatt per meters per Kelvin. The minimum heat exchanger area required for this operation is dash. So, given a double pipe part of the heat exchanger, we have to find the heat exchanger area. Let's just consider this is the inner. This is the tube of the double pipe heat exchanger. This is the outer pipe. Now we have been given oil flows with a flow rate of 1000 kg per hour. Oil is being cooled, so that is looking at and as is equal to 1000 kg per hour. The inlet temperature is 70 degrees Celsius and it goes to 40 degrees Celsius. Water is used as a coolant and since this is a counter current, we enter from this side. Temperature is 25 degrees Celsius and it exits at 40 degrees Celsius. If I had to draw a temperature profile, it will look somewhat like this. This is x direction. Temperature of oil is increasing. It is 70 degrees Celsius, 40 degrees Celsius. And we have the water over here. Water will exit at 40 degrees Celsius and enter at 25 degrees Celsius. We can write the energy balance for this double pipe heat exchanger and it will be Q dot H is equal to Q dot C is equal to UA delta T LMTD. Let's just write this heat balance for this hot fluid that is oil. So it will be M dot H into CE delta T UA delta T LMTD. Let's just calculate the log mean temperature difference. LMTD will be delta T1 minus delta T2 ln of delta T1 upon delta T2. Here delta T1 will be this temperature difference, so that is 30 degrees Celsius, and delta T2 is this temperature difference, so that's it. That is 15 degrees Celsius. So the LMTD we can write this as 15 upon initial log of 2, and it will come around 21.64 degrees Celsius. So we can replace this in the formula. So mass flow here will given as 1000 kg per hour. So we can change this 1000 kg per hour into kg per second. It will become 1000.3600 to Cp here will be given for the oil as 2. Temperature difference of the oil is 70 minus 40, that is 30 degrees Celsius. Is equal to U heat transfer coefficient here we given as 0.2 into area we have to find the log mean temperature difference we have found it out as 21.64. Basically that is the area, the heat exchanger area will be given as this is 3000 upon 3621.64. This will come around 3.85 meters square. So the minimum heat exchanger area required for this operation is 3.85 meters square. You can report the final answer as 3.85. We looked at this question 34 related to double pipe counterflow heat exchanger to calculate the minimum heat exchanger area. So now we will look on to another question. Okay, so this is question 40 from GATE 2016, in which we have been given a shell and tube heat exchanger. Then the energy balance of the equation we have been given the Nusselt's number correlation, and then we have been given two cases. In the first case, the mass flow rate is the same, and in the second case, the mass flow rate of the cold fluid is doubled. And we have to find that if we change the mass flow rate to double, what will be the change in outlet temperature of the cold fluid. So let's look at this. Let's look at the video solution of this question 40. Hello everyone. We are solving question 40 of grade 26 mechanical engineering paper. And the question is, in a 1-1 fast shell and tube heat exchanger, steam is condensing in the cell side at a temperature Ts of 135 degrees Celsius, and the cold fluid is heated from a temperature T1 of 20 degrees Celsius to a temperature T2 of 90 degrees Celsius. The energy balance for this heat exchanger is given by this equation, where U is the overall heat transfer coefficient, A is the heat transfer area, and what is the mass flow rate of the cold fluid, and Cp is its specific heat. Tube side fluid is a turbulent flow, and the heat transfer coefficient can be estimated from the following equation, where N is the Nusselt's number, R is the Reynolds number, P is the Prandtl number. The condensing heat transfer coefficient in the cell side is significantly higher than the tube side heat transfer coefficient. The resistance of the wall to heat transfer is negligible. If only the mass flow rate of the cold fluid is double, what is the outlet temperature of cold fluid at a steady state? So, in this given question, we have been given a single pass and selective heat exchanger. Let's just consider single tube over here, and this will be my shell side. So steam is condensing in the cell side at the temperature of Ts. Here, Ts is given as 135 degrees Celsius. Similarly, the cold fluid is heated from a temperature of 20 degrees Celsius to 90 degrees Celsius. So Tc will give us 20 degrees Celsius, and Tc out, that is the cold fluid outlet temperature, we have been given as 90 degrees Celsius. And then we have been given the energy balance. This energy balance equation, as well as we have been provided this correlation of Nusselt's Reynolds number and Prandtl number. From the given, we have been given the condensing heat transfer coefficient in the cell side significantly higher than the tube side heat transfer coefficient. So the cell side heat transfer coefficient will be based on the outer side of the tube, so we call it as H0, and it is significantly higher than the tube side heat transfer coefficient, HI. And the resistance of the wall to heat transfer is negligible. Okay, so can you please
the mass flow of the cold fluid is doubled. Therefore, the second case resistance M2 C for cold fluid is twice of the cold fluid mass flow rate in the first case. So this is all the information we have been given. So the heat transfer coefficient, we can write it as for the inner side as Ui equal to 1 upon, this is my convection resistance based on the inner side heat transfer coefficient. Similarly, this will be my conduction resistance to the wall, that is Ei upon A ALM plus Ei upon E naught into 1 upon H naught. So this is my convection resistance, this is my conduction resistance to wall, and this we have been given in the question, that is the resistance to the wall to the heat transfer is negligible. So this entire term is negligible, so let's just consider it as 0. And also we have been given this correlation H naught is very greater than Hi, so that is we can write that like 1 upon H naught is very less than 1 upon Hi. Also this area of inner side area will be less than the outer side area, that is Ei is less than E naught. So that is this term will also be very less as compared to this term, so we can neglect this term. So from this overall heat transfer coefficient, we can write this as Ui 1 upon N is equal to Xi. That is, the overall heat transfer coefficient is equal to the heat transfer coefficient of the inner side, that is Hi. Now we can find this Hi by using this Nusselt's number correlation. So let's just do that. Nusselt's number is given as H, then the inside diameter into K. This is written as 0.023. This Reynolds number we can write it as rho V upon mu. Inside diameter upon mu 2.8. Similarly, Prandtl number will be Cpu by K. Let's just keep it as PR only. Is equal to 1 by 3. So we can write this Nusselt's number as 0.023. Let's just change these parameters into mass flow rate terms, that is m dot, so that we can have the correlation between Nusselt's number and mass flow rate, and later on we can calculate the correlation between Hi and the mass flow rate. So by using this density and the velocity, you can change this into mass flow rate as Bi to mass m dot upon Ei is my the heat transfer area of the inner side upon 2.8 into Prandtl number of 1 by 3. So this diameter will remain constant, area of the inner side will also remain constant, mu will also remain constant. Only the variable is m dot, that is the mass flow rate. So from this we can write the Nusselt's numbers directly proportional to m dot raised to 0.8. So that is we can write it as mu is equal to k times m dot raised to 0.8. That is here the correlation between Nusselt's number and the mass flow rate. And then we can use this Nusselt's number as Hd by K and write it as Hdi upon K is equal to T dot into 0.8. Again, here this H we can replace it by U as we have found out from over here. So that will give us Ui is equal to Ui into Di upon K equal to K times of m dot of 0.8. Let's just call this constant as K dash. So here Di is also constant, this thermal conductivity will also remain constant. So that is we can write as Ui will become K double dash of m dot h to 0.8. that is our overall heat transfer coefficient, is proportional to m dot raised to 0.8. From the real side, we have this information. Now let's just use this equation. Now, so that is this equation is ln of Ts minus T1 upon Ts minus T2 is equal to UA m dot Cp. Here we know that U is proportional to m dot raised to 0.8, so that is you can write it as 3 double s 0.8 into area on MCP. This can be written as, again this area and Cp will remain constant, so we just call it as a triple dash is equal to m dot raised to 0.8 minus 1 will become minus of 0.2. That is ln of Ts minus T1 and Ts minus T2 is equal to 3 days of m raised to minus of 0.2. So now we have this correlation that we will be using to find the outlet temperature for the second case in which the mass flow rate is double. So let's just write it over here. In case 1, the mass flow was m dot. T1 we were given as 20 degrees Celsius, T2 we are given as 90 degrees Celsius, Ts we are given as 135 degrees Celsius from over here. And in the second case, the mass flow rate is double, that is m2 will become twice of m1. So that we found out from here, mass flow rate is double. Rest all, that is T2 we have to find. T1 and Ts will remain the same. So that is, we will use this equation for both the cases to find our T2, that is outlet temperature. So for case 1, you can write this as ln of Ts minus T1 upon Ts minus T2. This is for case 1. Similarly, LS of Ts minus T1 upon Ts minus T2 for case 2. So this is the term that we have to find out. Will be equal to a triple dash n1 plus 2 upon triple dash n2 raised to minus of 0.2. So now Ts we were given as 135 degrees Celsius. So we just replace those numerical values. 135 minus 90 upon 135 minus 90 upon ln of 135 minus 20 upon 135 minus T2. T2 we have to find. This will get cancelled out, and m1 upon m2, that will become m1 upon m2 raised to minus of 0.2. This is visible, that is, we can write this as ln of 115 upon 135 minus T2. This will go over this side and this will come into the numerator. So this term will become ln of 115 upon 45 into minus of 2. 1 by 2 raised to minus of 0.28075, and this will become 0.93, so this term will become 0.8167. That is ln of 1 upon 135 minus 52. Ultimately, this we can solve. From here we can solve this and find the T2 as 84.192 degrees Celsius. That is for the second case in which the mass flow rate is doubled, the outlet temperature of the tube will be 84.192 degrees Celsius. So from the given option, we can select option B as the correct answer.
So we looked up at this question 40 from GATE 2016 Chemical Engineering paper. If you have any doubts in any of the questions discussed today, then you can write it in chat box or unmute yourself and speak up. I guess this was the last question. So today we looked at, I think, around 6 to 7 questions. So the first question was related to radiation shield. So this kind of question was asked multiple times in GATE. So where we have to just straight away use this formula. Then this is a fairly straightforward question related to lump heat capacity analysis that is also widely asked in GATE question papers. Then these questions are related to this Nusselt's number correlation. This is a simple question related to this formula, the relation between absorptivity, transmittivity and reflectivity. Then this is related to conduction across the wall and the effect of insulation. Then this is related to double pipe counterflow heat exchanger. Then this last question was related to shelling tube heat exchanger. If you have any doubts in any of the question discussed, then you can write or we can end today's session. Thank you for joining. I will be here for a couple of minutes. If you have doubt, then you can ask. Alright. Okay, so if none of you have any doubts, then we can end today's call. Thank you everyone for joining. Bye.